IBM Quantum's mission is to bring useful quantum computing to the world. We started in 2016 by bringing the first quantum systems into the cloud, available for everyone to play with it. Because we needed to be fast, we started not just bringing them into the cloud, but producing them. Physical design, manufacturing, control systems, low-level software stack, bringing them into the cloud. We have a consulting team. So like full spectrum error mitigation. Oh, and by the way, the 3 NIST standards, we co-authored them for post-quantum crypto. And we have a practice for helping you implement that. So where are we today? This shows like circuit size and circuit width, and we're at this left lower corner. This is what we get with our current devices. There is some evolution coming over the next years. What we expect that will happen over the next 1-2 years is that we see quantum advantage. It's not that we will create quantum advantage, but someone using our systems will create quantum advantage or will be able to claim that. So improving on quality of hardware, improving on software algorithms, improving on error mitigation will get us there. Now, there's a whole set of workloads and problems that require much more, and I'm going to spend a few minutes on that. This is the road to fault-tolerant quantum computing. And we've been on the journey also for a bit now. And I think it was 2 years back. The LDPC code brought a major improvement over the surface code, like bringing down the number of physical qubits needed for fault tolerance by a factor of 10. Then we see several steps on the way to quantum computing in a fault tolerance manner. And I'm just going to mention that we demonstrated each of these steps fundamentally. It's all backed by papers. And so we don't think it's a scientific hard problem anymore. We think it's a hard engineering problem from this point on, which is great because that gives us credibility on this roadmap. So first of all, we need, for this surface code, we need a 6-way connectivity. That's going to be challenging on a 2D chip on one level. So we got to find something there. But 6-way gets us to the right code. Then bridging the qubits on that chip requires further distances. And so we're looking at 6 millimeters, 7 millimeters, 8, 10, 14 millimeters, have tunable couplers between qubits with decent quality, as we have measured. And that gives us the ability to achieve this 6-way connectivity. Now, we need to go to different planes on the chip. And that is the next challenge, like breaking this 2-dimensional structures and going 3-dimensional in the chip. And just recently, we've published some improvements on real-time decoding to create like quantum memory. Now, you see on the left-hand side, this is our current Heron architecture. The red rectangles are tunable couplers. The grayish things are qubits. That is what we have today. To go 6-way connected, it needs to look like the right-hand side. And we see the complexity, and I think as Herman mentioned, or who mentioned it? Was earlier today, like you can't manually do that anymore, right? You need more professional chip development for that. So that's coming, it's on our roadmap. And then we will have several building blocks that we can plug together to really achieve that fault-tolerant architecture. So we have building blocks of 12 logical qubits, and that's sort of the memory. Then we have logical processing units on top of that, built on top of that, operating on these Torus codes on the protected memory. And then we have the third set, which is kind of universal adapters, which is also qubits that are connected through L couplers. L couplers are extend to about 1 meter, roughly, in length, and that's the vehicle to connect these modules out of one fridge to the next fridge. And so that gives us the ability to create the large-scale fault-tolerant system. And the last piece is magic state factory. So magic state distillation will be needed to achieve a universal quantum gate set. So all of that is backed by papers, by work. We just need to plug this together. And so the concrete steps to do that are actually Loon in this year, 6-way connectivity. It shows the C couplers, which are the couplers on chip. Then Kookaburra next year will give us longer C couplers. It will give us real-time decoding, and it will be the first LPU approach. Cockatoo in 2027 will give us a demonstration of this long-range connectivity between these modules. And Starling in 2028 will be the first demonstration of fault-tolerant quantum computer, roughly at hundreds of logical qubits. And then moving on, that will be made available to clients 2029. 2033, there will be the next generation called Blue Jay, the order of thousands of logical qubits and billions of 2-qubit gates of circuit size. So we are building this right now. That is a photography of the Quantum Data Center in Poughkeepsie in upstate New York. It looks like a rendering. This is a real photography. And we do have some renderings as well because we don't have the 2029 state just yet. But I've seen some photos. The lighting already is there in Poughkeepsie, so we did the first step. And so that's the Starling, and you can see like the dimension that we expect to have by 2029 and 2033. So it's not football field, it's more basketball courts in terms of size. And so that is what we expect to see over the next couple of years. Thank you.